Hello and welcome to another video. In this video we're going to be working on find valid matrix given row and column sums. And this one we're given two arrays, row sum and column sum, where the row sum is the sum of a row and the column sum is the sum of a column. And you have to make a matrix out of this where the matrix fulfills these criteria. And it's guaranteed there's at least one, and you have to make one. So here in this example, this first row has a sum of 3, the second row has a sum of 8, first column has a sum of 4, second column has a sum of 7. So this would be the matrix. Second, for the second one, same thing. So this is 5, 7, 10, and this is 8, 6, 8. And notice in the examples, a lot of times there's zeros and like big numbers. So that's part of it. But let's say we have this random thing here. So basically the way I went with this is the constraints are kind of big. So I was trying to figure out like what kind of algorithms will be possible. So if the constraints are kind of big, if you have to manually try a bunch of numbers, there's going to be like a lot of criteria there. Like maybe you have some sorted rows or something. But any kind of like DP, just try numbers, there's going to be way too many things. Because here, so if this is 500, that means the row is 500 by 500, or the matrix, which is like 225 and then this, right? So this is like 10 to the 4th, 10 to the 5th. So basically an n-squared solution would fail. And if an n-squared solution will fail, like if you can't even do an n-squared on the matrix, then like you have to have something simple, like an n log n or a linear, some kind of greedy thing. So I was thinking of like, how can I do some kind of like sorting, maybe sorting columns or sorting rows on like the biggest or something, and then greedy as well. And it turns out the greedy one is the one you want. And this problem's not the best, but basically let's say you know like a greedy solution, or you don't know, you're trying some greedy thing. Okay, so if we were to try to do this in a greedy way, like what could be a strategy? So maybe one strategy could be like, let's just try to fill out, so for every row, we'll just try to fill out the column that needs the most. So let's just try to maximize that. So like here, we could say like, okay, we'll just put an 8 here, and then we have 1 left, so we'll put it in this column because this one needs more than this one. So this one is done, this one needs 4 more, this one needs 3 more. So because this one needs more, then for the second row, we'll put in 4, and then we're done with that row, and then we can put in this here. So this does work, and this is like one of the ways that works. Basically, there's a bunch of ways that work as long as you don't put in too little numbers into these. So as long as you put in as much as possible, like you try to maybe go by like the biggest column, try to maximize, then the next one try to maximize, and the next one try to maximize. Because this number equals this number, anything works as long as you just put in as much as possible into every spot. But the better solution that's easier to code is instead of doing that, instead of picking the biggest column, we can just go in order. It doesn't really matter if we fill out the biggest column first. We can just go in order and in every cell try to put in as much as we can. So in this cell, we can't put in more than 5 because this column total is 5. So we'll put in 5 here, and then we have 4 left, so we can put in 4. And then we don't have anything left for the row. Then here, this column's filled, and we have 4 left here, so we can put in 4 like this. And then finally, for the last one, you can put in this. So basically, the idea is you just go cell by cell, and you take the minimum of whatever's left in the row and the column to fill, and put that in there. And that will ensure that, that's like one of the ways you can get the greedy solution. So I do think this problem's kind of not the best, because the problem with it is, like, once you recognize the greedy solution, the coding is super easy, but recognizing is not super easy. So, but the main intuition for it is figure out like, okay, if I just try to manually get these numbers in some sort of DP way, these constraints are way too big. So it has to be some greedy or sorting or something. Yeah, so that's what we'll code. So we'll say rows equals row sum length columns and then we'll have a result. Yeah. And the dimensions will be rows and columns. And we can loop through our matrix. And the columns as well. So yeah, now that like the order of the cells we visit doesn't matter as long as we just try to put in as much as we can every time we get there. Then we'll just say result the minimum of the row total left there and the column total left there, because that's all we can put in. So row and column sum column. And then we have to, whatever we put in, we have to subtract from these. So you have to say we're going to subtract this number. So at row column. Just realize this needs to be a row column. Okay. And this needs to be a subtract. And the same thing for the column sum. Okay. And then we just return the result here. All right. And there we go. So this is going to be pretty simple for complexity. M by n and O of 1, because we just made a result matrix. We didn't use anything else. So yeah, not the best problem, I'd say, but hopefully you understood it. And I do think this acceptance rate is really high just because people probably like looked at the solution and they're like, oh yeah, it's pretty easy to code after that. But I would recommend for these problems, yeah, basically recognize that like if there wasn't a greedy thing, most algorithms would be either very complicated or the dimensions would need to be way smaller. Like if you need to try numbers manually or something, it's going to be way smaller than this dimensions for it to pass. Yeah, that's going to be all for this one. So if you liked it, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.